Good day, everyone. My name is Sebastián Jorquera. I'm a PhD student at the University of Chile, and today I'm going to present you the talk Are Companions Creating the Structures in Protoplanetary Disks Observed by ALMA? This is a project I've been working on under the guidance of Laura Perez and Gael Chauvin. So, as an introduction, let me show you this image that some of you might already know. If not, this is a plot showing the distribution of exoplanets identified as of today. The x-axis is the distance of the planet to the star in astronomical units, and the y-axis is the planetary mass. And as you can see in this plot, there is a great diversity of planetary systems and architectures. We have hot Jupiters, we have super Earths, and we have many other configurations of these systems that can be identified. And the problem is that there is no universal mechanism to explain this diversity. There is no one unique mechanism that could explain this great difference in planetary systems. We have to resort to different theories and different models to try to explain what we are observing. If, for example, we go to the formation of these systems, these are the three main theories of planetary formation: core accretion, gravitational instability, and gravity-driven fragmentation. The advantage of using these three different models is that each of these models explains the evolution of planets and the formation of planets with different properties, such as mass and separation, and in different timescales. So by combining the three of them, we can attempt to explain the observations that we are getting today. But how can we be sure that these models are correct? Well, one option is to check the signatures of these planets into their surroundings, into their environments, the protoplanetary disks. With this idea in mind, the DICHAP survey was born. This was a survey of 20 protoplanetary disks observed with ALMA, with the goal of linking the properties of protoplanetary disks with the initial conditions of planetary systems. The idea or the criteria to observe or to select these targets was to select targets where resolution of 5 AU was possible to obtain, because this was essential for identifying the disk substructures, and to observe mainly young systems. The average age of the sample is 1 megayear. Why is this important? Because this time scale it's believed that it's linked to the early stages of planetary formation. And here are the results of this survey. And as you can see, in almost all the targets, we can observe different substructures, such as bright rings of material, dark gaps that seems to be depleted. In some cases, there are spiral arms. And the question is, are the planets responsible for these structures? Are these structures linked with the presence of companions? And the answer is, well, maybe. Shang et al. Performed hydrodynamical simulations of the disk considering the presence of a companion at different locations, and these simulations show that the observed structures can actually be produced by a companion that, for example, is carving some of the gaps observed. The problem is that due to the uncertainties on the disk properties, such as viscosity or grain size distribution, there is a wide range of planetary masses that could produce these structures. So without a proper characterization of these planets or of these properties, it's not possible to give a good constraint on the properties of the other. So a next step is to attempt to observe these planets so we can characterize them, and with that check with the planetary formation theories, and also to check with the models and to try to constrain the disk properties. For this, we did a follow-up with the NACO instrument, a BLT of the discharge sample, and this is the project I've been working on and I will focus on today. Using BLT NACO, we obtain L prime observations that allow us to obtain a high contrast in the mid-infrared, which is favorable for planet detection, and The only problem was that only 12 objects of the discharge sample were observable because of a magnitude limitation due to the systems of the instrument. And how do we try to detect these planets? We use a technique called angular differential imaging. And this consists that using a pupil tracking mode in the NACO BLT, we can follow an object in the sky during the night, and the field of view will appear to be rotating because of the pupil tracking mode. Assuming that the signal from the emission from the star is stable, this rotation won't affect the signal from the star. But if there is a planet, a point source orbiting the star, this planet will appear to be moving around the star due to the relative movement of the field of view. What we do is then we obtain many different frames, many different observations of the target, and we construct an artificial frame obtained with the median of each pixel. With this, we recreate the signal from the star, or the image from the star, without the planet, because since the planet is moving, when we calculate the median, it's not going to appear in this artificial frame. We subtract this artificial frame from the original frames, and with this we aim to remove the signal from the star and to keep the signal from the planet, which the frames are then derotated and stacked, so we can get a final observation with hopefully the signal from the planet. So here's an example of this reduction. As you can see, the NADI, which is non-ADI, I mean the original observations, we have the signal from the star and the disk. And in all the different algorithms that we use, we can actually remove quite a good amount of the signal from the star. We can go into the inner regions, but we can study the surroundings of the disk. And now, what are our main results? What did we observe? Well, first, for RU loop, we detected a point source observed at 174 astronomical units, and based on the signal of this point source, we derive a mass of 2.2 Jupiter masses. To check if this object was a real planetary companion or a background object, we study the proper motion of this object using archival data from 2017. In this graph, the orange dots are the expected proper motion of a bound companion, and the blue dots are the real proper motion of the target based on our data. As you can see, there is no correlation between the two, so we assume that this is in fact a background object, but further observations are needed to definitely confirm this. Another interesting result is the case of Elias 24. In here you can see, pointed with an arrow, a point source observed at around 55 astronomical units. And an important feature of this is that it is located in one of the gaps of the disk. So it's possible that if it is a real companion, it can be carving this gap and be producing this structure. To check for the possible properties of this object, we estimate its mass based on comparisons with evolutionary models. We did a conversion from its luminosity to its mass, and we obtain a 5 Jupiter mass for this target based on these models. The problem is that even if it can be considered quite a high mass for a planet, when we study the detection probability maps that we obtain from our observations, we actually have a very low detection probability. So it's difficult to be certain if it is a real detection or only an artifact induced by the reduction. But there is an alternative scenario. We study the possibility that an actively accreting protoplanet is in there. Considering the signal of an actively accreting protoplanet, which consists of the signal of the planet itself plus a circumplanetary disk, there is actually the possibility that the mass could range from 0.5 Jupiter masses to 5 Jupiter masses, depending on the accretion rate and the properties of the circumplanetary disk and the disk and this protoplanetary disk itself. So, further given these alternative scenarios and these probabilities of detection, it's very important to have follow-up observations of this target, so we can determine if our observations was real or if it was in fact only an artifact induced by the reduction. So, our conclusions. 12 objects were observed and analyzed with NACO. At larger distances, we lack detections for all the targets, which allow us to rule out the presence of massive companions from 5 to 8 Jupiter masses or higher, depending on the disk. The detection around early loop is regarded as a background object, as I mentioned earlier. There is a possible companion detected at Elias 24. The mass range depends on the possible accretion rate if we assume it is actively accreting. If not, we have to compare with evolutionary models and test different possibilities to check for its mass. And finally, as I mentioned earlier, a follow-up with other instruments is necessary to attempt detection of lower mass planets in all the targets, and in the case of Elias 24, to confirm the presence of this candidate. Thank you very much for your attention, and hope you have a great day.